Hi, this is Josh from Over the Shoulder Coding, where I help you prepare for software engineering interviews by guiding you through solving real problems. In this series, I will walk you through the Advent of Code 2018 challenge day by day. Day 12, Subterranean Sustainability. The year 518 is significantly more underground than your history books implied. Either that, or you've arrived in a vast cavern network under the North Pole. After exploring a little, you discover a long tunnel that contains a row of small pots as far as you can see to your left and right. A few of them contain plants. Someone is trying to grow things in these geothermally heated caves. The pots are numbered with 0 in front of you. To the left, the pots are numbered -1, -2, -3, and so on. To the right, 1, 2, and 3. Your puzzle input contains a list of pots from 0 to the right and whether they do or do not currently contain a plant. The # or hashtag is for if they do contain a plant, and the period is for if they do not contain a plant in the initial state. For example, an initial state of #,#,#, indicates that the pods 0, 3, and 4 currently contain plants. Your puzzle input also contains some notes you find on a nearby table. Someone has been trying to figure out how these plants spread to nearby pots. Based on the notes, for each generation of plants, a given pot has or does not have a plant based on whether that pot and the 2 pots on either side of it had a plant in the last generation. These are written as LLCRRN, where L are the pots to the left and C is the current pot being considered. R are the pots to the right, and N is whether the current pot will have a plant in the next generation. For example, a note like ... yields ... means that a pot that contains a plant but with no plants within 2 pots of it on the left or the right will not have a plant in it during the next generation. A note like ... yielding ... means that an empty pot with 2 plants to the left and 2 plants to the right will also remain empty in the next generation. A note like ... yields ... means that a pot that has a plant in a given generation and 1 plant immediately to the left and 1 plant in the pot 2 to the right will yield a plant in the next generation, meaning that that pattern is sustainable. So these are not sustainable patterns because they yield a dot. This is a sustainable pattern because it yields a plant. It's not clear what these plants are for, but you're sure it's important. So you'd like to make sure the current configuration of plants is sustainable by determining what will happen after 20 generations. For example, given the following input with an initial state of these plants, so this is the 0 pot, and these are other pots going down the line, and these notes or rules for what patterns are sustainable, this is what the next 20 generations will look like. So the first generation is just the input state. So this was the input state, #, starting at pot 0. And we have a couple pots on the left because we can grow more plants on either end. This is what the progression of generations looks like. After 1 generation, only 7 plants remain. The one in pot 0 here matched this rule, and the one in pot 4 matched this rule. So you can see this pot got a plant because it matched this rule. In this example, after 20 generations, the pots shown as # contain plants, the furthest left of which is pot -2, this one, and the furthest right of which is pot 34. Adding up all the numbers of plant-containing pots after the 20th generation produces 325. After 20 generations, what is the sum of the number of all pots which contain a plant. So, which contain a plant. This is our puzzle input. We have this initial state and these notes or rules. So some of the notes produce a no plant in the next generation in that pot, and some of the rules do produce a plant in that pot in the next generation. So what we need to do is to come up with a way where we can quickly look up these rules and determine whether a center pot here in this configuration will have a plant in the next generation. So if we have a pot and we find its neighbors to the left and the neighbors to the right, we want to do a really quick lookup to see whether or not we will be able to have a plant in that pot in the next generation. So let's say we take this pot right here. Well, we want to look up this pattern of pound, pound, dot, dot, dot. And we could loop over all of the rules, which would take a long time. But we have a data structure already that we know is a lookup data structure that is made exactly for this, and it's going to give us O of 1 lookup, and that's a map or a Python dictionary. And so we can immediately look up this pattern, which is the same configuration here, and know that yes, it will yield a plant in the next generation. And we need to do that for all of the pots in the tunnel. And we have two edge cases as well. One is if a pot is on the end. For instance, these two pots here, they're on the end, so the pots on the left are implied to have no plants in them. So this pot here at the very left edge has a pattern of dot, dot, pound, pound, dot. So this pattern. And you can see that this being the center has these two on the right, and it's not going to yield a plant in the next generation. And this first pot here has a pattern of dot, pound, pound, dot, dot, which will yield a pot in the next generation. Now, that edge case happens for both of these pots on the ends here. There's another edge case though for the pots on the end that aren't in the initial state or aren't in the current state, that aren't even described. So a pot here, a -1 pot, would have a configuration of dot, 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 pound, pound. So it would have, we're looking at the pot that would be here, the -1 pot, and we're implying that the two pots to the left are also dots, and these two pots, the 0 and the 1 pot, are potted with plants. And so this -1 pot is going to have a plant in the next generation. And we can see that in some of the examples here. So here the 0 pot in the initial state is a pound. And as we go down some generations, this -1 pot that wasn't even described in the initial state turns into a pot that has a plant. So those are the two edge cases for pots that we know already we need to be wary of. So we found some edge cases already just looking at the question overall, and we know that we want to encapsulate these rules in some sort of a dictionary map. What else do we notice about this problem off the bat? Well, they're asking for multiple iterations, right? So we're going to iterate a next generation 20 times. So we have to make a data structure that represents the current state, and then apply all the rules to those items in the current state to generate the next generation. Go to that next generation, apply those same rules again, and make the next generation, so on and so forth, for 20 generations. So what is that data structure that we're applying all these rules over. This is an ordered set of pots going from 0 to n on the right and 0 to negative n over on the left. But we don't have a predefined set. We don't have a predefined limit on the number of pots. In fact, it's infinite. We can have infinite pots stretching all the way to the right, infinite pots stretching all the way to the left. So using a fixed length list or array isn't really that helpful here. And a hash set could be kind of helpful because it doesn't have a fixed length and it has O of 1 lookup. But what we should probably use in this situation is a linked list, because you can form additional nodes or additional pots to the left or to the right, and you might remove pots on the left. For example, here on generation 16, this -2 pot does have a plant in it, but then the next generation it doesn't. You might not want to be keeping track of that information forever and ever if you don't have a sustainable generation, if it collapses on itself and you end up keeping a bunch of dots, just keeping them around. All right, so that's kind of how we're going to tackle the problem. We're going to store these rules in a hash map. We're going to parse this initial state and make a linked list of pots representing this initial state. And then we're going to iterate over all of these pots and make the next generation, then substitute and start using that list and make a next generation off that list and a next generation off that list. So let's give that a shot. So I've described that approach, and we're going to break it down into the individual classes that we're going to make. So first we have to come up with what a representation of a pot is. And the most important thing about a pot is whether or not it has a plant. So it's a $ for yes and a dot for no. And since we're using a linked list, a doubly linked list in this case, we're going to have the pots know what their neighbors are. So self.left is going to be the pot to the left, the negative, and the self.right is going to be the pot to the right, or the next one, positive. And the reason we don't need to know the left, so in the case of rule execution, right, we get the left, the left of the left, and the right of the right, is because we can just say self.left.left, because we're getting the pot to the left and accessing the left in that one. And that's actually what we're going to do in describing the pot configuration. So we need to figure out what pattern this pot is, right? So we're going to start from the left, the most left pot. If the pot has a left and it's not on the edge case, remember we described the edge case here on the initial state. If you're on the end, you don't have a left pot. So if you don't have a left pot, we enter the else case where we just say that pot is implied to be empty. If you do have a left pot, we check if that left pot has a left pot and get the value of whether it has a plant or not. So for instance, if you're somewhere in the middle here and you are looking at, maybe this pattern, and that's your center, and you're looking at the left and it has a left, you're saying, does that have a plant? If so, indicate that it has a plant, otherwise indicate that it doesn't. And you're doing that for the one immediately to your left afterwards, then you're doing yourself, then you're doing it to your right, and then your right's right. And then that's configuration. So if we try it out, so we try it out and we just start with the pot by itself. And so this is the center pot. It has no lefts and no rights. We're going to get all dots. And if we say true that it has a plant, then we see that it is indicated with a pound, right? And if we say pot.left equals pot true, we're going to get 1 to the left, right? And so we're going to need that when we say, okay, this is my center pot. I need to find my configuration and then look it up in this map of rules to determine whether or not the next generation is going to have a pot. So that's what we do here. We're saying, will the next generation have a plant? And we're saying, get the configuration like we just did. And if the configuration is in this hash map of rules, so we're going to map this rule, this configuration as a rule to whether or not it has a plant. So this is going to be a map of the configuration of 5-character string to true or false. So true if it's a pound sign, meaning the next generation has a plant. False if it's a dot, meaning the next generation does not have a plant. So those are the most important things that a plant can do. And for convenience sake, I say that if we're setting the pot to the right of our current pot, we're going to set the pot to be current.right or self.right. And we're also going to set that pot's left to be our self. So for instance, if we're constructing this initial state and I'm here and I'm saying the next pot is an empty pot, I can say self.setRight to be an empty pot. And I'm also going to connect that pot to myself. This is something we're going to do many times. And it's just a little bit more convenient if we have these two things together. That way we don't repeat ourselves and forget to link our linked list. And then the other edge case is if you're at the end, you see these 3 pots here, we could actually save space by just writing 1 dot and implying that these 2 at the end are actually empty. So that's another thing we're going to do. And we're going to pop those empty pots from the end. So if we are on the very end, for instance here, if we're on the very end here, we don't have a pot to our right. So if we have a pot to our left, that means that we're on the rightmost end. And we're going to say our left, which is this pot here, we're going to say this dot right is none. And so nothing's going to be referencing this anymore. So this isn't going to be in the list anymore. And same thing, if we are on the leftmost end of the list and this ends up being empty pot, we're going to say if self.right, meaning that we are on the end of the list, self.right.left equals none. So we're going to remove ourselves from the list. So those are the pots. So pots are nodes and they contain whether or not they have a plant in the pot. So the next thing is the tunnel. And in the tunnel, we have the 0 pot because we always want to keep track of where our 0 is because we're going to have to sum these up at the end. So that's why it's important to keep track of the 0 pot. And we also keep track of the head of the list. That way it's easy to print it out like this. And we initialize our tunnel, the pots in the tunnel, this initial state, based on this initial state string that gets passed in. So if the first character in the string is a pound, then we set true, meaning the pot starts out with has plant being true. Otherwise, we say false. The plant does not exist in the pot, and we start out with an empty pot in the 0 pot. And then for I in range 1 through the rest of the initial state string, we make a new pot with the same condition. If it's a pound sign, we put a pot with a plant. Otherwise, we say there's a pot without a plant. And we say current pot that's set right, new pot. So let's say we just made the 0 pot and we just entered the for loop. We make a new pot that's empty because this is a dot and not a pound. and then we say current pot, set the right pot to be this empty pot, and we link these two. Remember, in this method here, we set the current pot's right to be this empty pot and this empty pot's left to be the current pot. And then we move our current pot over to be current pot dot right. So now this one pot here is our current pot, and we make this new pot and link these two and then move over here. Then we make this new pot, link these two, and move over. And we do that for the entire initial state string. That's how we create our initial condition and represent it as pots. And then we take in the rules as a map, and we have a couple other small settings that I'll show you later. Verbose is for whether or not we print every time, and generations is just to keep track of the generations. And I made a helper function to print the tunnel. So basically we'll walk from the head through the current string. So every time we have a pot, we say, does it have a pound sign or a dot? So we go backwards. So if current pot has a plant, we add the pound sign, otherwise we add the dot, and then we move on to the next pot, and then we end up printing that tunnel string. And then we have the next generation method. This is the method that's going to tick us from one generation to another. And basically what we did here is we generated the current generation going left from the zero pot. So in this example, it would be everything on this side. And then we also did the same thing symmetrically mirrored on the right-hand side. So what we did was we started at the zero pot and set that as our current pot. And we started the zero pot for the next generation. So here's the zero pot that's current pot. Here's the zero pot that's next generation zero. And we say it's a new pot that will have a plant if it meets the rules for those. And we say that the current for the next generation starts at the next generation zero. So we're going to go left. So while current pot has left pots on its left-hand side, we're going to do the exact same thing. So we're going to say if current pot has a left one, we're going to move our current to the current's left. So our current pot is going to be -1. We're going to make a new pot to represent that pot in the next generation, and then link the two here on set left, and then move the next generation over to that new pot. And we're going to do that until current has no more pots. Then we're going to check for the pots that were implied empty on the current generation. So these pots aren't actually even represented in that initial state. We're going to have to check if those will become pots in the future. So in this example, generation 2 to generation 3, we actually had a pot go from not even existing in the current state to being a pot and having a plant in the next generation. So that's what we need to do. So what we do is we say current pot.set left. We actually create that empty pot and set it and link it on the left-hand side. And we move that as our new current in this line. And then we make a new pot in the next generation and see if it will contain a plant, and set that as the left of the previous next generation current and move the next generation current to that pot. And then we do that again for the second one to the left. But in some cases, we go from having a pot to having a pot that is empty, so we can trim the pots on the left. And that's what we do in line 97. So while the next generation pots do not have a plant, so if we're going from generation 3 to generation 4, these on the left don't have a plant. We're going to trim them, popping them from the end and going right. So we're going to start at the very end and then go right until our next generation pot is equal to the next generation pot 0. We never want to lose track of the 0 pot. So that's why we stop on this condition here. And so here we generate the left-hand side first, And so the leftmost pot that remains is going to be the head of the next generation. So we're setting that here in line 100. And then we reset at 0, and we do the right-hand side. So we do this whole thing over for the right-hand side. So we generate all the next generation pots that already have current pots. So we do this, and then we find the next generation pots that don't currently have pots and see if they will have pots in the future, like going from Gen 1 to Gen 2. And then we trim the right-hand side if any of those pots end up becoming empty. And then we prepare for the next generation. So we say that the new 0 pot is going to be the next generation 0. So that's the new current 0. We increment our generations. If we had verbose on, we would print what the tunnel looks like now. So we'd print this state. And just for record keeping, we say we grew n generations and the current sum is whatever the current sum is. And we get the current sum by starting with a running sum of 0 and going left. So for each pot that we move 1 left, we're incrementing our counter. So we're saying this is the -1 pot, or this is the -2 pot, -3 pot. And if it ends up being this is the -2 pot on line 20, then we would say if it has a plant, we add that counter value, which is negative when we're going left, to the running sum. And as we're going right, we do the same thing. So while we have pots to the right, we increment the counter. If any of those pots have a plant, we add it to the sum. We add that pot's index value, which is our counter, to the running sum. And we don't need to worry about checking the 0 pot, whether it has a plant or not, because adding 0 to the sum is not going to make any difference. So that's how we're going to sum the value of our parts. And parsing input, we've covered this many times in this series. I'm using regex to grab the initial state. So we're searching for a grouping of either pound signs or period signs. And we're going to grab that grouping, which is going to be our group 1, as the initial state string that we parse. And we're also going to read in all these lines of 5 characters, this configuration here, 5 characters of pound signs or dots, and 1 character of pound signs or dots after this arrow, meaning whether or not it is going to have a plant in the future or not. We make our map of rules, and with the regex, we are able to say if rule group 2, which is this column here, if it is a pound, meaning that it will for sure have a plant in the next generation, we add it to our map of rules. If not, we leave it out. We don't need to store it. And we read the next line. So we only add rules that will yield pots with plants. We don't add rules that will not yield pots with plants. And that is because in the we'll have plant method of a pot, we say if the configuration exists in rules, return true, otherwise return false. So the fact that it exists in the rules means that there will be a plant in the next generation. We're not going to store this. So that's why we made that choice there. We're saving space, and that's good. Cool. So we're able to parse the input, generate the initial condition of current pots, and we're also getting all the rules. So let's do part 1. So part 1, we're parsing the input, we're setting verbose to true, we're going to print that initial tunnel, and then we're going to iterate 20 generations and sum it. So you can see here, this is what it looks like. Let's look at the example input and match it up. So here, looks like this. Looks pretty similar, right? So let's pick a random line. Line 9, generation 9, pound, pound, dot, dot, pound, dot, dot, pound, pound, pound. Matches up exactly. So we'll run it for input text, and we sum it, and we get 3421, which turns out to be the right answer. So we solve part 1 by simply just iterating through all the rules, getting the next generation, continuing for 20 generations, and then summing that at the end. Pretty straightforward. If you like that, give me a thumbs up. If you have any questions, please ask them in the comments down below, and I'll try to get back to them. Let's move on to part 2. So in part 2, you realize that 20 generations aren't enough. After all, these plants will need to last another 1,500 years to even reach your timeline, not to mention your future. After 50 billion generations, what is the sum of the numbers of all pots which contain a plant? So we could let this program run for 50,000. So let's see what that looks like even, right? And it's just running and running and running and running and running. It's probably going to take forever. So what does this mean? Well, there's probably some trick, right? Maybe it's growing at a certain rate and you can calculate that, or there's a pattern. Maybe it's stagnated, or maybe it ended up being 0, right? You should just run this. In an interview, you should just run this and see what happens. And you can say, oh, I guess that there's going to be a pattern. Maybe it's linear, maybe it's geometric or exponential. You don't know. But there's no way that you're going to run 50,000 iterations or 50 billion iterations in an interview. So let's look at what happens between generation 1431 and 1432. So in generation 1431, the sum is 74,176. In generation 1432, the sum is 74,227. So let's just see what the difference is between these two generations. The difference is 51. Maybe that's the difference between these two generations. So 74329 minus 74278. So it is. So after a certain point, all these generations are growing linearly. So in one generation, we had some fluctuation. It started out 2,500, then it went down, then it went up, then it went down. But after a few hundred generations, it's growing pretty consistently, right? So if we go back to 1471 or 72 or whatever it was, right? We know that after this point, everything's growing linearly. So we just need to find 50,000 or 50 billion minus 1472, the remaining generations after 1472, times 51, since it grows 51 at every generation, plus 74,267, which is the current remaining generations, which is the current sum at generation 1472. So 50 billion minus 1472 times 51 plus 76,267 is this really large number, which is the right answer. And you can see here, we're still running this program. There's no way you're going to answer this in an interview, right? Your interviewer would stop you and say, hey, let's look at what's going on. So just a quick tip that if something seems really, really large, probably won't brute force it. You probably need another way to find the answer. Thanks for watching this video. Please support me on Patreon so I can make more videos. If you missed the previous video, please click here to review it and subscribe and ring the notification bell so you will know when the next video comes out. If you want to see me solve other problems, please comment down below. Thanks, and I'll see you later.